Alright, guys, moving on. Graphing. We are going to graph roses today. Yes, we're going to graph rose curves. And in order to graph these, we're going to need to put it on the polar coordinate system, which I'll probably attach that on Google Classroom as well. All the other graphs that you had on the last quiz, you really just got circles or lines, which you can just graph on your normal coordinate, your XY coordinate plane. So what we're going to look at, for this first video, we're just going to look at the sine one. But what makes this different than the graphs where you got circles and lines, okay, these are the form of the equations that we're going to deal with. This n, the number that multiplies the angle, is now going to be bigger than 1. All right, so for all the ones that we did before, when you had it in polar form and you got a circle or line, n was always 1. In this case, it's going to be bigger than 1. And when you graph it on the polar coordinate plane, it's actually going to give you a rose. Now, this really sums everything up. It gives you a good synopsis on how you graph sine and cosine, and n really kind of drives everything. So we're going to look at if n is even, then the graph and the rose petals are going to be symmetric to all of these, x-axis, y-axis, and origin. If n is odd, which is what we're going to look at for this first video, then if it's cosine and n is odd, it's symmetric to the x-axis. Right? Easy way to think of that is cosine is always x. It always equals x in the unit circle. If n is odd, and in the equation you have sine, then these rose curves are going to be symmetric to the y-axis. All right, and this is actually what we're going to look at. And there's examples here, and we'll go over some of the other examples in other videos. But if we look, this one that I circled, here's an example. This is where n is 3, so n is odd. And here's the other part. How many petals does it have? If n is odd, then whatever n is, that's how many petals you're going to get. So if you look, since n is odd and it's 3, see how I get 3 petals here? Now when you graph, you're really only going to get 3 points. You're going to get the point that's at the top of each petal. You're not going to get any of these points here to see how wide it goes. All right, I'm not going to be that picky. And then you can see how you're going to start right here at the origin. So I guess you could say that's a 4th point. All right, so let's take a look at an example where we have sine, but n is going to be odd. So if n is odd and it's sine, it's going to be symmetric about the y-axis. And since n is 3, then we're going to have 3 petals. And that's what's going to happen here. All right, now we're going to kind of go back to when we graphed sine and cosine waves. Remember we did max, min, equilibrium. Let's first do that. I'm going to put this right here. All right, let's put max. We have equilibrium, and we have minimum. All right. Now the good thing about this, there's no vertical shifts. So this is kind of the amplitude right here. So the max is going to be 4, minimum's -4, and the equilibrium 0. So those are the only values we're going to get for r, right? It's kind of replacing the y value. Now this is supposed to be theta right here. Okay, now number of petals, since this is odd, since n is 3, we're going to get n petals, which in this case is 3. And then symmetry for this, it's going to be symmetric to the y-axis. This is really going to help us get the graph of this more quickly if I know this. All right, now the period, our normal period for a sine wave is 2 pi, right, in the unit circle. Now remember we would do the period was 2 pi over b. Well, in this case, it's like we're replacing that b with this, the n. So the period is going to be 2 pi over n, which is 2 pi over 3. Now again, going back to graph, remember we did increments. It's your period divided by 4. So in this case, it's 2 pi over 3 divided by 4. Well, that would be the same thing if you multiplied the bottom by 4. or multiplied it by 1/4. So let's say you would get 2 pi over 12, which is pi over 6. All right. Now, in order to figure out what values we're going to plug in for theta, we're really using the increments. All right. Now, we're going to start at 0. Now, I'm going to exaggerate this. I'm going to go from 0 to 2 pi. So I'm going to have 0. And then since the increments are pi over 6, I'm going to add pi over 6. So we'll go pi over 6. If I add pi over 6 to pi over 6, I get pi over 3. And I'm kind of skipping this work right here. But if I added, that's what, 2 pi over 6. If I added pi over 6 to that, I get 3 pi over 6, which is pi over 2. I add pi over 6 to that, I get 4 pi over 6, which is 2 pi over 3. And I'm just going to keep going just to kind of save time. We would get 5 pi over 6. So this is what I get if I keep adding pi over 6. Then I get pi. Then I get 7 pi over 6. Add pi over 6 to that, I'm going to get 4 pi over 3. Add pi over 6 to that, I get 3 pi over 2. Add pi over 6 to that, we get 5 pi over 3. Add pi over 6 to that, we get 11 pi over 6. And if I add pi over 6 to that, I get 12 pi over 6, which is 2 pi. All right. Now, I'm telling you, you're not going to get all of these angles right here. All right. And you're going to see why. And we're going to use symmetry. We're only going to get, since we have 3 petals, we're only going to get 3 points, which is going to be the tip of each petal for the rose. All right. Now, the other thing to remember is, remember, sine always starts at the equilibrium. Let's make this a little bit smaller so we can fit everything on here. Sine always starts at the equilibrium. So I'm going to follow the pattern here. This is where sine starts, right, at 0. So that first point we're going to get 0. Since it's positive for the amplitude, we're going to go up to the max. So then it's 4. I'm just going to follow the pattern. It's going to come back down to the equilibrium of 0. Then we go to the minimum of -4. We come back up to the equilibrium of 0. Go to the max of 4. Down to the equilibrium of 0. Down to the minimum of -4. Back up to 0. Up to the max of 4. Back down to the equilibrium. Then back down to the minimum, and then we end at where we started at 0. All right? Okay, now we're going to graph these. Now, every single point where r is 0 for all of these, think of it, it doesn't matter. It doesn't matter what the angle is. If r is 0, it's right here. It's at the origin. So you're always going to have a point at the origin. Now, if I were to graph this, pi over 6, 4. Okay, I'm going to go to pi over 6 right here, and I go to the 4th circle. So 1, 2, 3, 4. So it's right here. All right, now that's going to be a petal, right? That's one petal right there. Whoops, kind of sloppy. Again, I don't care how wide it is. Then when I go to here, pi over 2, -4. Well, pi over 2 is here, but since the radius is negative, it moves 180 degrees all the way to here at 3 pi over 2. So at the 4th circle, 3 pi over 2, 1, 2, 3, 4, we're right here. That's a second petal. Okay, then if I go to this next one, 5 pi over 6, 4, we're right here. And I leave that at the 4th circle, that point. Let's go 1, 2, 3, 4. So it's right here. That's the 3rd petal. Now, if you look, you have 3 petals, and it's symmetric to the y-axis, right? If you fold this over, these lie on top of each other, and these cuts that petal in half, so it's symmetric to the y-axis. All right? If you kept going, like if I did 7 pi over 6, -4, 7 pi over 6 is here, but since it's negative, you would flip it, and it's actually that point right there. If you did this, 3 pi over 2, 4, you already... 3 pi over 2, 4, you already have that point right there. So once you get to this point, you really don't even need to do this. I just did it just to exaggerate. If you kept going, you're going to get these same 3 points and also that 4th point of the origin. All right? So a lot of this was review with max, min, and equilibrium and getting the period and the increments. But the first thing you should do is get this. Figure out what n is. That gives you how many petals and what it's symmetric to.